Okay, I'd like to thank the organizers for putting this up and letting me speak. And what I'll talk with you about is pressure and non-equilibrium systems. There will be a specific class of non-equilibrium systems, which are called now, they have a name, they're called active systems. And I'll give you some experimental motivation. So there'll be no fluctuations. I'll be going back to the basic question of an equation of state for these systems and trying to look for it. So there's been a growing body of people which have been working with me on this. So Alex Solon, Julian Tayor, Meran Kardar, Mike Cates, Aparna Bhaskaran, Yuan Philly. So most of what I'll tell you is actually from the paper with them, which you can find here. And if I have time, I'll tell you about some unpublished results with with some permutation of the authors above. It is also with Nikolai and Raphaël Vautourier. And if I tell you about this thing, that it means that you haven't understood anything of what I've told you. So hopefully I won't get there. Okay, so the outline of my talk is as following. I'll start with motivation. What are the experimental systems which people have looked at before or looking today, which motivate the models that I'll be looking at. Then I'll do a very short recap of what we mean by equilibrium equations of state, something we all know, but I'll just want to highlight the things that will be important for my talk. And then I'll tell you about the models that I'll be looking at. Specifically, they're called run and tumble models or active Brownian particles, and they each correspond roughly to the experiments that I'll show in the beginning, of course neglecting lots of important physics, but I won't highlight that. Then I'll discuss the question of an equation of state in these systems, and I'll start even with the ideal gas of non-interacting particles. And there's a reason that I'm highlighting, I've put this equation of state in gray, and that's the punchline of the talk. So if you're falling asleep now, there's generically no equation of state for these systems. And I'll show you some possible experimental consequences of this thing. And then I'll tell you about some other properties of active systems. And this I won't get to. I'll actually discuss something else. Okay, so systems of interest are active matter. Essentially, it's slightly different from the scenario where we're driving a system out of equilibrium by coupling it to two boundaries. We have a collection of particles which are each absorbing energy and dissipating into some large environment that we ignore, and they're being driven locally out of equilibrium. So if you want, we're really breaking detail balance on the local scale and not by some connecting to some boundary reservoirs. So there are examples of these things which are abundant. This is a really old movie from the Howard Berg lab who's done tons of work on E. coli. So these blurred figures are E. coli bacteria. Their size is about 1 micron. And they move as a velocity. They have these flagella which push them in the fluid. And they move with a velocity of a few micrometers per second. And once in a while, I'll show you the movie in a second. So these are the flagella. Once in a while, they stop and they change direction randomly, and that's called a tumble. So this is the movie if it works. So you're supposed to see them roughly moving in a straight line and then reorienting. So what I want to do is take this system, which is obviously at a low Reynolds numbers regime, and think that I'm putting it in a box and I'm measuring the pressure of these guys. Okay, and actually I'll stress it more later. I'm actually measuring the osmotic pressure for reasons that will become clear in a few seconds. Okay, this is a more modern, if you don't like biology, and I know that some people are biology. This is an artificial version of a similar model that was done in the Dave Pine lab at NYU. So these are colloids, which are, the details are given here, but the important thing is that they're covered with plastic, and there's a small hole lift in which there's essentially iron and oxidants that once exposed to the solution, which is H2O2, and you shine light on it, and there's a chemical reaction occurring at that hole, which drives the particle in a specific direction. So this is the movie. So this is light off, just Brownian motion, the textbook Brownian motion. And now lights on, and they start being driven in a given direction. And of course, there's some randomness in the orientation of these colloids, so their orientation slowly diffuses about. So the previous model, when I'll do the theory, it will be the model corresponding to it will be run and tumble particles, and these are called active Brownian particles. It's just they're very similar in spirit, but just two names. Okay, so again, the fact that they're out of equilibrium is this drive that's either because E. coli is eating or that because there's some chemical reaction driving this thing inside the solution. Okay, so note that when I first saw people working on this, I thought, oh, this is not really interesting because if you coarse the grain, it just looked like non-interacting Brownian particle. Who cares? Okay, and so it's an ideal gas. Who cares? And I'll try to convince you that that's actually there are cases where this is not the case. So the steady state, if you look at it in a uniform environment, it's completely boring. Nothing exciting happening. Okay, so back to this basic statistical mechanics. So the basic thing you do is you look for an equation of state. So the most famous one you know is the ideal gas one. And there's something that we take for granted, we don't think about it anymore, is that if we want to know the pressure of a specific system in equilibrium, we only have to know bulk properties of the system. So you tell me bulk properties, I'm okay, you can replace the boundary with whatever you want, you can replace it rubber, metal, glass, whatever you do, I get always the same pressure. So to calculate the pressure, you can do several things. The thing that we always do when we're taught stat mech is we calculate the free energy, we differentiate it with respect to the volume, and that gives you the pressure. But there's another calculation that you could do. You could just calculate the force acting on the wall. So the force acting on the wall is given by the integral. If I have one species of particle, it's given by the integral. I'm doing it along, say, a wall along the x direction. So I'm doing an integral over the density of particles inside the wall times the force exerted by the particles on the wall. And L is the position of the wall. So throughout the talk, I will be thinking about a large system, mostly in 2-dimension, and it's coupled to some wall whose length scale is much, much smaller than the length scale of the system, so I don't have to consider finite size effects. So there's some wall, and what I do is I just calculate the force acting on the wall, and it's sort of, when you look at this integral, you sort of think, okay, this is density, of course it depends on the potential. This is the potential, a derivative of the potential, but there's some magic where this integral, when we calculate it, doesn't depend on the potential. So whatever potential I put inside, I get the same result. And what we do usually is just put an infinite wall, so that's where the calculations are easier, at least for the free energy. Okay, so if anybody insists, I could prove this is a 3-line calculation, but I guess you could take it as a homework exercise. Did anybody do the one from yesterday? Okay. Okay, so what I'm going to do, for these active particles, I want to calculate the pressure, so I don't have a free energy, so the only thing I can do is just calculate the force acting on the wall. So what I'm going to do is just place a wall at one end of the system, say a spring, or you could imagine a wall covered with glass or rubber or whatever you want. And I'm going to calculate this integral, and I'm going to calculate the force acting on the wall. Yes?
Yeah. Maybe you get, why can't you use the virials here?
Well, because you'll see, let's discuss it afterwards, because actually when you take these expressions and you try to connect, you find out that there's extra terms. Okay, we can discuss it later. Okay, I don't want to discuss it now. Okay, so the two models, so now I want to, I've introduced the motivation, so now I want to introduce the models. They're called run and tumble particles or active Brownian particles, and sort of motivated by the experiments. What I'm going to do in 2D mostly is, you can think about bacteria. I'm going to take a bunch of ellipses, and each ellipse has an arrow glued to it. And these ellipses move with a velocity, which is the drive velocity, which depends on the direction of the arrow. So if you want to think about it, it's an XY model, off lattice, no interactions between the spins right now. I'll put them later maybe. and they're just driven in the direction that the arrows are pointing. So you released the XY spins free. Sorry. Okay, so the velocity of these guys is the activity. It better be that when I turn this activity to 0, I'm back to equilibrium. So this will be my test that everything comes back to equilibrium. And of course, on top of this, I'm going to add rotational diffusion of these arrows. So this is the change of direction in these Dave Pine experiments. I'll add diffusion of the center of mass just to have sanity checks that I'm back in equilibrium when I have to go to equilibrium. And then I'll add tumbles, which is events where you stop after an average amount of time, just Poisson, in a Poisson manner, and you randomly orient your arrow in a new direction and move in the new direction. And all these details, I'm just showing all of them. The result that we show don't depend on whichever combination of these things you do. The important thing will be, as you'll see, nothing will be very important. Okay, so I've described the model without writing equations. I want to write down simple equations in a second. But the important thing is that we want to calculate what's happening inside the wall. So I have to tell you what's happening to these particles inside the wall. So this is my wall, and this is my particle inside the wall. So I want to write the currents for the particle inside the wall. So this is the current associated with the center of mass of this ellipse. So we have the activity, which is the velocity originating from this arrow that's driving it in a specific direction. Then we have the force that's acting. I used to have anyway. This is the mobility, and this is just the force acting because I feel the potential of the wall. So this is the wall influence. And then, of course, I have diffusion of the center of mass. And then I have to worry also about the degrees of freedom of this angle. And these, as I've told you, diffuse. I can add tumbles. I'm not writing them here. So they diffuse. So this is my rotational diffusion of the arrow. But then if I have an ellipse inside the wall, then it's obvious that there are torques which are acting on this guy, right? So if the ellipse is just pointing towards the wall, there's no torque acting on it. If it's pointing up, if the arrow is pointing up, again, there's no torque on it. So there's a component that's a torque that depends in general on the shape of the particle and on the potential. But it's something that I can actually calculate. Okay? So just to illustrate, so I can add tumbles. So just to illustrate that this is a case which you can do while I'm talking probably. So you take an ellipse, you put it in a harmonic potential. So this is an harmonic potential that starts at L, and it has a strength lambda. And you could have guessed this without doing any calculation, actually. The torque acting on the ellipse is given by the strength of the potential. A measure of how anisotropic this ellipse is, A is the long axis and B is the short axis, and sine 2 theta. That's what I told you before. If it's pointing this way, there's no torque. If it's pointing this way, there's no torque. Yes?
I don't see the tumble.
The tumble, I can add yeah, it's not in the current. You can add it. It's just a constant term in the master equation. Easy. Okay? I haven't written it down. You're right. I wrote just add tumble. Okay, so you can see that the only case that as you expect, if you have a circle, then there's no torque acting on this guy. Okay, so some comments which are actually important. First is low Reynolds number, which I think is less important. The most important thing is that this model doesn't conserve anything. Not energy, of course, but more important, I'm not coupling to a momentum conserving field. I'm not taking account of the fluid around it, or around myself. So really, if I want to justify this calculation, I want to think of something either moving next to a surface or that I have no momentum conservation, at least next to the boundary. So I'm really thinking about osmotic pressure at the moment. We don't know. We're thinking about what happens when you're coupled to a momentum conserving field. That's a much harder problem technically. Okay, so to calculate pressure, you just do this, you take the model, you have the master equations. For this audience, it's simple enough to write them down, and you do this calculation, and this is the expression that you get. It looks a bit horrifying, but I'll guide you through it. It's actually very simple. This term is just the diffusion of the center of mass divided by the mobility, which has a t here for Anyway, this is just my blunder times the density. So this term is the ideal gas term. And you can see that when I turn off the activity, when the velocity goes to 0, then I'm back to equilibrium. So this is my sanity check that everything is okay. Then I have another term that you might have guessed from dimensional analysis as an effective temperature. It's the velocity squared divided by the mobility times the tumble rate and the diffusion constant. So that's something that you would have guessed, that, you know, I told you large length scale, it looks like an equilibrium system. So let me guess the temperature by dimensional analysis, and I'm done. Okay? But then we have this term, which is much more interesting. It goes at the integral of the torque inside the integral inside the wall of the torque sine theta, the angle and the density of particles is position x with angle theta. And the interesting thing is that now rho, this density depends on the potential. The torque, of course, depends on the potential. So the pressure depends on the potential that I'm putting inside the wall. Okay? So that means that there's no equation of state. I can't express the force acting by those particles on the wall just in terms of bulk properties of the system. You really have to tell me all the nasty details of which wall you've put inside and what everything, and then I can tell you what the force acting on the wall is. So just to illustrate this, if you take the ellipses in an harmonic potential, so this is my ellipses, this is the torque, you can do the calculation. There's a small approximation that we're doing. So anyway, the details are not important. And this is for the case where we have no tumbles and no translational diffusion. And you can get an expression for the pressure. And you can see that the important thing is that it's 1 minus an exponential of this dimensional number, which is the important thing, which depends on the wall potential, mobility, the anisotropy, so this is, if you want, the torque times the mobility, divided by the rotational diffusion of these guys. So if this number is much, much larger than 1, yeah.
Before it was of order V, and now it's of order V squared.
That was the correction. When you actually carry out the full calculation, that's what you get.
The correction before the torque.
Yeah, but don't forget that you have you have V appearing in the row, etc. Okay. So just to illustrate what this equation means, this is anyway the normalized pressure. It doesn't really matter. What you want to focus on is probably active Brownian particles, but this is just to illustrate that it works similarly for other models. So this is what I'm doing is I'm increasing the strength of the potential and measuring the force acting on the wall. And what you can see is that when I increase the force acting, the strength of the potential, the force acting on the wall drops. And it's just not dropping by a small correction. It's dropping by a whole lot. Okay, so essentially I'm almost killing in this model the pressure completely. And when you think about it for 2 seconds, so the more rigid the wall in this case, the smaller the pressure. Okay? So if you think about it for a second, it's actually fairly easy to understand intuitively. We have these ellipses which are penetrating the wall. And if I have a small torque, then these ellipses can penetrate deep inside the wall and their direction can keep more normal to the wall. So they're applying more force on the wall. But if I have a large torque acting on these guys, so they get turned pointing up very, very quickly, and the force that they're actually exerting on the wall becomes weaker and weaker. So as I make the force steeper and steeper, the force becomes smaller. Yeah?
What's the distinction between your model and the model of gas of hard ellipsoids, just aligning elastic?
Well, this is the activity. So you see that's the only, looks like a minor issue, but the fact that I have this V that's sitting inside my equations of motion, which in the presence of a potential actually violates detail balance, that's easy to show fluctuation dissipation if you want, makes it a completely different thing. So that's what I was emphasizing before. Despite the fact that if you look at a uniform system, it's completely boring. Once you put a potential, things get interesting, and it means specifically, recall that when I put the activity to 0, I got back an equation of state. Okay? So it's really the activity that's killing all the things that you know from equilibrium. Okay, so it's just this fact.
How does the density profile look like near the wall?
The density, okay, so it depends on the shape of the wall, but it actually tends to be, because they penetrate into the wall, it tends to be larger inside the wall. So there's a bump inside the wall. I can show you later pictures. So what's happening is that you're affecting the orientation field of these arrows inside the wall, and that's actually changing the force that they exert on the wall, and that's therefore the pressure is different. And you could also put the arrows on the different direction and have the force increase with increasing strength of potential. So just to recap, it's something that we know from non-equilibrium for a long time. If you check the temperature of a non-equilibrium system with different thermostats, you could define thermostats in various ways, then you find out that different thermostats which agree at equilibrium, they suddenly disagree out of equilibrium.
Thermometers.
What did I say?
Thermostats.
Okay, thermometers, sorry. Thank you. Slip, okay. And here we're saying the same thing is also true for pressure. So if you want to measure the pressure of these guys, you buy pressure measuring equipment from various companies, and different equipment would give you different results. That's a fact of life, unless they've all sort of tuned their potential to be exactly the same. Okay, so you could ask, okay, so what are the consequences of this guy, of this thing? So one thing you could do is go back to this simple equilibrium experiment where you take a gas and you put a partition in the middle. And you know in equilibrium that if I just chuck a partition in the middle of the gas, nothing's happening with this wall. It's just staying put. It's not moving to any direction. And that's true even if I cover one side with a rug and the other side by glass, it's still staying at the same position because the pressure depends only on bulk properties. And now I have to go here. So it's a very quick movie for technical reasons which don't interest you. Okay. Okay, so this is the same experiment with a soft wall on the right, and I'll do it again, and a hard wall on the right. And you can see that the wall is being pushed to the right because the force acting on one side of this partition is different from the force acting on the other. And now I have to go back again. Sorry. So what happens is if you wait, it stops at a new equilibrium position with a different pressure on both sides. You can actually calculate the location of the partition. It's not for the harmonic. Yeah, you can calculate the density on both sides of the partition. And they depend on the potential on both sides of the wall. Okay, yeah. Sorry?
Boundary condition.
So there's two symmetric walls on this side, which are just harmonic potentials. Yeah, and there are just two harmonic potentials here, and they're just much steeper. Okay, so it's just a simple thing you can do, and so another sort of this is even sillier. So you take a gas of these guys and you put one wall which is very, very soft and the other wall which is very, very hard, and you want to hold it in place. And you have to exert different forces on different sides of the system. So this is something that's obviously from the fact that I have a momentum sink in my model and will probably go away when I have momentum, not probably, will go away when I have momentum conservation. Making Mr. Newton happy. Okay, there's one specific limit which we've actually been interested in is when you have these spherical particles, and when you recover an equation of state, because you might say that this is a class of models where I might make some more serious attempts at the thermodynamics of these systems. So it's interesting to ask what happens in this case. So the first thing you could do is ask what happens. Sorry, I've been a bit unorganized. So what happens when I take this case where I have an equation of state? Remember, so when I have spherical, it's just magic. I have an equation of state. And the first thing you could ask is what happens when I add interactions between these guys? Do I still have an equation of state, or does, sorry, let me repeat this. If I have spherical particles, do I always have an equation of state, or this is very sensitive to the interactions between the particles themselves? Okay, so what we do is we take these spherical particles and we add interactions between them, and we look at 3 different cases. So the first case is it's sort of a toy model of a general class of model, which is called the Vichik model. So we have these particles moving about. They have no hardcore interactions between them. That's just so we can do calculations in an easier way. But they tend to align each other. So this is back to the XY model. But now, so XY model where they're moving in the direction of the arrow and still aligning with each other, but they're spherical. So when I turn off these interactions, I have an equation of state. So the equations of motion are for the center of mass for each of these particles is given just by this Langevin equation. And for the angles of each of the particle, this is the aligning force between them, which generally depends on the distance between them, etc. And you can actually write down an expression for the pressure of the system in terms of bulk, in terms of correlators, not bulk correlators, sorry. And you have this integral. Again, the details don't matter. The important thing is that it depends on the correlator between the probability of finding a particle at point r and angle theta and finding it at r prime and at position theta prime, which clearly depend on the wall potential. So that means that once I introduce aligning interactions between the particles, I again lose the equation of state. So just to illustrate this, these are numerics for a specific choice of this aligning force. So this is, you just align within a given radius and you normalize it by the number of neighbors. And this is the pressure as a function of density, sort of the usual plot that we do when we teach stat mech. And what you can see is that in the non-interacting case, you have one curve because it's spheres and you have an equation of state. But for the interacting case, you get for each strength of the potential, you get a different curve. So that tells you that there's no equation of state just because I introduced aligning interactions between the particle. So it's very, very sensitive. It's not only the torques, but it's something, it's very, very sensitive. We don't have a great understanding of when you have an equation of state and when not. This is another example. It's sort of popular in this active matter field. It's called quorum sensing. And the idea is that you modulate your velocity depending on your local density. So there's some, you look at some radius around you, and if the radius is, if the density is increasing, you typically bring down your velocity. So sort of like a crowding effect. So if I move in a, like this morning where the road was free, we could move very, very quickly. But if we move in the center of the city, we were crowded. So that's supposed to model that. And again, I just plot the pressure as a function of the density. And you can see that, again, we have 3 curves, which are different. So there's no equation of state. OK?
This is one-dimensional?
This is two. You can do one-dimensional analogs of these things. This is a case that we've actually worked a lot on, and I won't discuss. If you want details, you can ask me, or they're here. So if you take these spheres, which have no torque, and you take only pairwise interactions, so you have interactions which are symmetric, they don't depend on the direction of the arrow anymore, then you find out that you can actually, you get an equation of state. So this is illustrated here numerically. I'm plotting the pressure as a function of density for different potentials. And you find out that they collapse one on top of the other. And we can actually, in this case, write down an equation of state which depends on bulk correlators. So if you measure bulk correlators, I can tell you the force acting on the wall, and that's where there's some new physics that you find out. Okay, so you've been awfully quiet. Questions? Yeah.
For the first type of interaction, what do you have when you have a flocking order?
Yeah, we don't see any dependence on the flocking ordering. Okay, at the moment, but we haven't investigated that very carefully. Okay? Other questions? Okay, so far I've cheated a bit. Why? Because when we say no equation of state, we mean any wall shape. And I've always used flat walls. That's what we did. So what I want to do is, and this is unpublished, I want to look at non-flat walls. So I'm taking the same system with now a wall which has some modulation. So we have the fluid here, and there's a wall, but there's some wall structure along the system. And here, immediately you see that, so this is again the spheres, because I know that for anything that's not as non-interacting spheres, we've also checked it for the interaction with a pairwise potential. So I know that for these cases, I have potentially an equation of state. If I take ellipses, it's not very interesting because there's no equation of state. And what's plotted here, so this is the wall and this is the bulk of the system. You can see that the bulk is completely uniform. And what I'm plotting here is the density along the wall, which is now strongly modulated. This is very different from equilibrium, right? Because equilibrium equipotential lines have the same density. So here they're modulated just by the fact that they're active. And if you look carefully, this is, you probably can't see, but trust me that this is actually showing that there's local currents that you see in the system. So they're moving, they're creating sort of local vortices when there's a wall changing potential. And even more striking, if you look at the pressure, okay, not when you've seen this, it's less striking. When you look at the potential, then it's, so this is the potential normal to the wall. It depends on where you are along the wall. Okay, so it actually depends on where you are local to the wall. So it's actually, as you might have guessed, it's highest here and lowest here. Okay, so there's a magic that if you actually do the calculation for these systems, again, spherical or spherical with pairwise potential, and you calculate the average potential along a period of the wall potential, the average pressure along a period of the potential, then you recover an equation of state. So despite the fact that the pressure is modulated along the wall, when you do an integral over one period of the potential, then you recover this equation of state even when there are pairwise interactions or in the ideal gas case. And more striking, I'm not showing the data because I have 6 minutes and I knew this. This is true even for walls which are not up-down symmetric. So if you have a wall that sort of has really non-symmetric shape, sawtooth, then you might guess ratchets, and lo and behold, you find that you have edge currents, not like the quantum ones, but there's edge currents along the system, and there's a pressure that's actually perpendicular to the wall, so it's sort of pulling the wall down because of this. But nonetheless, when you calculate the pressure acting on the x direction and you integrate over a period, you get an equation of state. So there's some magic that's happening here. And the last thing I want to show you, before concluding, is that, so we had this wall. Let me go back. So we had this wall, and I told you that there's a high potential, high pressure here, and a weak pressure here. So what you could do is, it's sort of a natural thing to do, is you take this gas, and instead of putting a hard wall, as I did before, I put a flexible object inside. So I take my two-dimensional system, and I connect a polymer between two edges of the system. Okay? And now, I've just told you if I look from, so if this was the wall, I told you that the pressure here was higher than the pressure here. But now the wall is sort of open to both ways. So now the pressure here will be higher than the pressure here, but also higher than the pressure here. So you sort of expect an instability. So when I put the polymer inside the system, and very different than an equilibrium one, you expect this instability to grow, where you lose the just fluctuating shape of this polymer, and you get some structure. And this is a numerical simulation. So you see only the polymer. You don't see the active particles which are running around. And you can see that it's a slowly developing sort of a characteristic structure. And okay, we still don't understand this very well. We're looking at cases with bending rigidity and without bending rigidity. We think that we understand the beginning of the instability. We don't understand the late time evolution. It seems like it's coarsening, so the stable state is just one long wavelength thing, which is taking over the system. And it seems to be very, very slow coarsening, logarithmically slow. So, okay, so back to pressure and flat walls. So far I've told you about lack of equation of state with and without interactions. You could ask about other differences. And I have 3 minutes, so I'll only show one. In equilibrium, it's a magic that we take for granted is that pressure is always isotropic, even if when you think intuitively, you might think differently. For example, when the sound velocity is different along different directions, you might naively think that, okay, maybe the pressure is different along different directions, but we know that that's not true, and the question is what happens when you have an active system. So when you have bulk ordering, then people knew before that you could have an anisotropic pressure in these systems. I won't discuss how they measure the pressure. That's not important here. But you could wonder if there's an isotropic bulk and still anisotropic pressure. So the simplest example is that you take a velocity that depends on the angle, but in a way that it's periodic in pi. This way you don't have a net current inside the system. And it's actually a straightforward exercise to show that the bulk is completely isotropic, so it's completely boring and uninteresting. But nonetheless, when you calculate the pressure, so phi is the angle at which you place the wall, and you find out that it depends on the angle that you place the wall. And that's an illustration of this result. So we put the walls at different angles on the system, and you get a different force that's acting on them. So the last thing I'll show is we know that when pressure admits an equation of state, usually when you don't have an external field, then if you have a flux-free states, then it implies that your system is homogeneous. That's sort of our basic intuition. So what you could do is sort of counteract this. You could take this Pine experiment maybe and try weak light on one side and strong light on the other. So you have different velocities on the different sides of the system. And these are spherical particles. So if I check the force acting on here, there is an equation of state for these guys. But there's a jump in the pressure of this across the system, and nonetheless the steady state is flux-free. Okay, so that's another contrast between the equilibrium cases and the non-equilibrium cases, and numerics show that this is true in general for these systems. So to summarize in my last minute, in active systems, generically, the pressure depends on the wall potential, and there's just no equation of state. And this is sort of what we knew for temperature. What temperature is sort of this thermodynamic quantity, and we might take it naturally, and this is a mechanical quantity. So when I teach undergrad thermodynamics, I never stop for a second. I just tell them if there's equal forces, equal pressures, nothing happens. But specific cases, you have a well-defined equation of state, and you can obtain it even when you have interactions. These are actually very interesting, and as a case where you might actually build a theory which has some thermodynamic structure, maybe not. You can have anisotropic pressure when the velocity is not isotropic. You can have flux-free steady states with a pressure gradient. Curved walls lead to varying pressure along the wall, and you have an instability, generic instability. You just take a flexible object and put it in an active matter. There's a generic instability to modulations of this guy, and okay, this might be used as a probe to measure the properties of these active systems. So thank you very much for your time.
So questions? Let me check.
So if and what happens in like driven granular material, I mean, which is also kind of non-thermal, I mean, do you get something similar?
I don't know. Oh, this instability?
So like there also probably you don't have equation of state, right? I mean,
I don't know. There's so much time we have to check all these cases. We did look, the only case we did look, and so you take this simple model of an active filament, which people have calculated the force of an active filament for ages, and you put a wall inside, that it's acting on a wall with a potential, and you find out that the force it exerts depends on the wall potential. So even a simple actin filament exhibits that. So.
Systems, I think people talk of membrane curvature and also protein folding and so on, things like that. It looks like this could be a possible mechanism by varying degrees of activity in the system, or turning it on, you can produce curvatures in a system.
Yeah, so we've looked at this polymer with fixed ends. There's many people which looked at rings inside active media. And if you look at their movies, you can see a hint of this instability, but I don't think, because it's a ring, they didn't actually notice it. So this might help for protein folding. I think these are usually equilibrium problem. Oh, never mind. I don't want to speculate.
Okay, so thank you. No questions? Okay, thank you again.